I'm very glad to welcome you to this seminar series of the spring semester. Very glad to introduce our first speaker, Professor Christina Niterotaro. She is assistant professor in the CS department and faculty member of CERIAS. She does a lot of interesting work dealing with security and reliability for distributed computing systems and wireless network. So I will stop here and leave the floor to Christina.
Hello, everybody. I would like first to wish you a good semester, since this is the first seminar in our series, and we start much earlier at other schools, so we need a lot of stamina to go through the semester. So I hope that you're going to have a great semester. Today I will give a talk on security topics in wireless networks, and more particularly I want to focus on routing. And this is joint work with two groups of people. The first group is from Johns Hopkins University, the school where I got my PhD. And this involves Professor Baruch Auerbuch and three students and good friends of mine, Reza Kurmola, Dave Holmer, and Herb Rubens. And the second part of the talk is going to focus on work that I did here at Purdue University with two graduate students. Actually, one already graduated, Bogdan Cărbunar and Ioannis Ioannidis. Oops. Now, why wireless? Well, because wireless is a very exciting area today. And I'm not talking only from the research point of view. I'm talking from the point of view of, everyday life. Almost every people here in the room has a cell phone, has a laptop that is using wireless connection. Many of you probably an iPad or a PDA, and that also has a wireless connection. So from this point of view, wireless technology really created a paradigm shift in the way everyday activities are deployed, in the way business is it's pursued, and also the way teaching goes. I think it's really great to have a laptop with a wireless connection, and instead of saying in some dark lab in the basement, being in a much better environment, maybe a coffee shop or outside, depending on your preference. And there are several aspects of it. So the first one that really created a big impact was the Wi-Fi technology that allows us to deploy wireless LANs, and through some gateway get access to the internet. This really was, this I think was something that brought the attention to wireless to many people. Cellular networks have been around for a while, but what become more interesting is at the point when, besides just voice communication, you could do data and you could also do images. In fact, I'm originally from Romania, and I just came back from home, and well, Romania is not US, right? But I was very nicely surprised to see that I could get data access. You could get data transfers through a cellular network. And for me, it was really great. Just go get a wireless phone, a small cable, and I was on the internet and I could do my work. As opposed as, in going through the wired network, it will take months till they change the plugins. Don't ask me why it takes so long. It's just bureaucracy. So that was really, really great. And there are countries like Japan and Europe where you can also get more than just data. You can get images. You can get much better services. Now, more recently, and this is something that I think will be interesting not only for people interested in research, but also many of you that graduate and they're looking for jobs in industry. It's something that people call mesh networks. It's basically a way in which the goal is to provide some of that huge bandwidth that is out there on the wire cable, but you don't get it in your apartments. Most of you probably have a DSL connection, and I know that many of us are happy with it, but just imagine if instead of that DSL connection, you're going to have a much better connection. And there is a lot of interesting work in this direction. There are many companies that are working on providing this type of service. Research-wise, it brings new challenges. And as I said, this is something that is really exciting. Now, I'm mostly interested in security. And unlike many other services, security is something that is very difficult to touch it and to put your finger on, right? When you're talking about communication, you have your cell phone. If you don't have a good communication, you immediately know. The sound drops. You don't hear very well what's going on, or you cannot reach a person. Security, you kind of notice that, you notice its usefulness when it's not there, just because something bad happens. So that's not that's not really a good thing. Why is security important for wireless? Well, for instance, one service that is important is something called access control. And this is not particular to wireless, but for wireless communication, if you have an infrastructure or you have a network in which you don't control the access of people who get access to the network, that has another implication because the wireless medium is shared, which means that the more people you're going to have accessing the network, the quality of your server, your service will go down. So it's a good idea to have such a thing, not only for security purpose, but it has also other implications. Another security service that it's probably one of the most well-known, it's called confidentiality, which means that when I'm sending data over the network, nobody can understand that information, but whoever I want it to send to, which is the receiver. For wireless communication, the confidentiality is actually more important for wired networks, just because it is much easier to eavesdrop the communication. And the Pringle box that I have there, I just took it from some presentation that some people from Berkeley did some time ago, and that's exactly what they used to get their small antenna, which they could intercept wireless communication. Of course, if you don't care about the fact that other people can understand your data, that's a different story. Now, other things that are important, many wireless networks are so-called ad hoc networks, which means that the communication between a sender and the receiver takes place through intermediate hops. And the problem there is how much trust do you have with respect to forwarding your data in the intermediate hops. So this is something that you have to have in mind when you have such a network. Why? Because they see your data, they may collect it, they may use the information or sell it or whatever. And last but not least, I teach cryptography, and usually when we talk about cryptography, we care a lot about, cryptographic mechanisms. How do we protect all, data communication? And we don't pay attention to things that are actually sometimes can be more dangerous. And physical security is such a thing, because you can protect the communication over the network, do the most sophisticated algorithms. If somebody stole your computer and data that was stored in the computer is not protected, then your security is kind of gone. So physical security is particularly problematic or important for devices that have wireless communication, just because it happens that all these devices are very small. So it's very easy to, you can lose them, they can be stolen. And once such a device is stolen or it's captured by somebody that wants to perform some malicious action, it's going to be more difficult to defend against an attack coming from somebody that has a device that is authenticated. These are just some of the arguments why would you need security. There are many others, and I'm sure that any of you will be able to bring more on the table. Now, as I said, most of them are not necessarily specific to wireless communication. And we know for wired networks, we know how to deal with most of these problems. But we cannot just take whatever was done before, just take it, you just apply it to wireless networks and everything works mostly. And mostly this is because the environment is different. So you have to deal with several constraints. Mobility is one of them. The fact that we like wireless devices because they allow us to be everywhere, but that means that from the communication point of view, it's more difficult and security point of view, it's more difficult to provide these services. We also have constraints in terms of energy because most of these devices are battery operated. So you have to design protocols and services that are able to take this into account. And there are other things like the fact that the environment is, most of it is decentralized. Wireless communication is also very vulnerable to jamming. The physical layer, it's quite vulnerable, and that's something that also has to be taken into account. So this being said, what can adversary can do? Because this is really important when you're talking about security, to define what an attacker can do to disrupt your service. And there are different models of attackers. The one that I'm interested in is an attacker that can do pretty much anything. So from the communication point of view, he can capture devices, can attack the network from inside. Not only that can try to impersonate, modify, intercept data, but he can also, for instance, drop data, which is something that is quite difficult to get around. The fact that your data will never make it, which relates to availability. And today, this is probably one of the most challenging things that we have to deal with. Reliability and availability. The service is there, is running, your data makes it to the other point. And in the distributed systems community where I'm coming from, usually such an attacker that can pretty much do anything, so you cannot constrain it with what he can do. It's sometimes referred as a Byzantine adversary. Now, what I want to focus on this talk in this very big picture of all these wireless technologies and attacks and services that you need to provide, I want to focus on routing. And I want to show you how can you design routing protocols that are able to provide service even when parts of the nodes that are part of the delivering data are compromised and they just don't play the protocol correctly. And besides that, if time allows, of course, I want to show you how some of those techniques you can take them and apply them in other environments. And the environment that I have in mind is a hybrid network in which you have multi-hop wireless network and a cellular network, a cellular component. And as I said, with respect to trust, we trust the source and the destination. We make no assumptions about mobility, but we don't try, energy is not part of the game. We are not trying to save energy at this point. So what I want to do in the next few minutes is to give you an overview of, or give you more details about attacks that can happen in multi-hop wireless networks. And then I want to present you two protocols working in two different environments and show you how we can address some of the problems. And for the first protocol, I will also show you simulations in which we can see how the protocol really acts in the presence of attacks. So feel free and stop me at any time. I know that sometimes I tend to speak very fast, so if you have any questions, please ask. What's different about routing in wireless networks? Any of you took any wireless class? Okay, so what is different in wireless networks is the fact that the medium is shared, which means that whoever gets access to the more users you have, the quality of the service goes down, and you cannot, every time somebody accesses the network, that means that somebody else cannot send. This is the way the technology works. So in order to do that, you have to design protocols in which you send over the network only data that really must be sent. And when you are talking about routing, there is a lot of data that is sent around that is not user data. It's just data that allows you or helps the system to maintain these routes. In wired network, most of the protocols are so-called proactive protocols, which means I have or I don't have to send data, I'm going to maintain information about all the routes. So there is information about what are the routes available to reach specific hosts that goes in the network no matter what. This is perceived as a high overhead in wireless networks. So most of the wireless routing protocols have a different approach. They will try to establish a routing path only if, or a host will try to establish a routing path only if he needs to route that path. Otherwise, I don't care. I don't care about sending all this unuseful data about all the routing paths in the network when, because of the mobility, they may break anyway. So this is what on-demand means. I need to route, I will establish a path. How do I establish? Well, I will flood the network, sending a message saying, I am looking for this host or for this, usually for this host. I want to route to this host. Do you know how to reach it? Do you know how to reach it? When this particular message reaches the receiver, another flood will be reversed such that when the sender receives this message, the path is constructed and knows how he should route the message. Now, so this is the main mechanism. Again, because of the fact that we don't want to send data that is not useful, only the first such message will be processed by a host. Why? Because I can receive as a host, I can receive questions about another host from different paths because this is flooding. So this flooding means that everybody sends to everybody. And if I receive it from different paths, I'm going to process only the first one. And I'm going to send it further. The rest, I don't care about them. I just drop them. Now, once the path is established, of course, there are certain metrics used to decide which is the best path to send. And which is the best path to select in wireless, it's another long story. But right now, the two protocols that were standards, usually they use the shortest path, either by counting having a hop count or how many nodes you have in between. you do shorted paths instead of the metric. There is some node caching that goes that also is performed, and in addition to this, there is a mechanism that allows nodes to detect locally if routes were broken. So if nodes detect locally that, for instance, my route with him was broken and we have a direct connection, I'll detect it and let other people know such that they can reconfigure quickly and we don't go through the whole expensive route request thing. I want to give you some small examples. So the protocol that I want to tell you a little bit about is called DSR, or Dynamic Source Routing. And the way this protocol works, when like more specific, is if I need to send a message, if I need to discover a route, I need a message. I send a message that is called route request. Every node in between, when sees the first such message, and there is an identifier that is associated with its request, he looks if he has a route, he caches to know that in the future he doesn't need to look for that, and then he sends it further. When this reaches the destination sends back, I got my path. The message that makes it back is called route reply. Okay? Now for the maintenance, the message is called route error, and as I said, is detected locally. I am pinging periodically my neighbors. If they're not there, I decide they died, the link is broken, and I will generate a route error message and propagate it through the other hosts. Well, what can go wrong? In the description or in the design of DSR and what I described before, there is no protection, no security mechanism in place. So that means that the basic attack that anybody can conduct is trying to modify the messages, trying to inject other messages. This is what fabrication and modification attacks mean. And in general, these are attacks that can be easily defended by authenticating every packet that goes in the network, and by also having a mechanism that allows the receiver to detect that data wasn't modified in between, and this is called data integrity. This is authentication and integrity are the basic things that if you don't have them, don't even try to build any other security service. Your protocol or your service is very vulnerable. So this is this is nothing new. How can this translate with respect to routing? Well, if I can modify, I'm an intermediate node, and I see a flood request going to me or the reply. If I can modify the metric, and that metric allows the sender to decide which is the best path. If I can modify that metric on the packet and nobody can detect that I modified, I can control as an attacker, I can control the path selection. For example, I can make the path look longer or I can make the path look shorter. If I make the path looking longer, well, all that can happen is that most likely that path will not be selected, so I will get service from the system, but I don't do much work. So this is not a very destructive attack. It's more like a selfish behavior. But if I make the path very short, I can make sure that many paths, routing paths in the network will go through me, which means that then I have access to a lot of the data that goes in the network. What can I do with it? Well, it depends what my mood is that day, right? I can drop it, or I can use it for traffic analysis, or I can sell it to somebody else. So it's not good to have somebody controlling your path. This can also happen with respect to error messages. If I starting randomly generating, this guy is dead, is not here, and there is no way you can control that this message came from not from somebody authenticated, then you can start reconfiguring routes, and if you don't have an alternate path for that particular host, then you have to discover a new one. So you can create a lot of problems and a lot of instability in the system. But as I said, these are not the difficult attacks. This we know how to deal with, and they're specific to any protocol. There are some other attacks that are quite specific to wireless, and it's more difficult to deal with them. So one of them is something that is called wormhole attack. So the idea in a wormhole attack is that an adversary has the ability to establish, it's called a tunnel or a wormhole. It has two nodes, at least two nodes that he compromised, and he has the ability to tunnel packets through this connection much faster than if the packets will travel normally through the network. Now, how do you get such a tunnel? Well, by not playing, the easiest way to get it is by not playing the protocol correctly. Because of the way the wireless technology works, in order to avoid collisions, because in wireless, one of the big problems is that you cannot detect that a collision happened when two people try to send at the same time. So you try to avoid collisions happening. And the way the avoidance is implemented is by having all kinds of timeouts in the protocol. So I'm not going to send immediately, and I have to wait. Everybody has to wait certain amounts of time before sending certain type of data. So if I'm an attacker that I refuse to play the protocol, I can get my data much faster than the others because I made it through the network, but nobody else can send. And what this type of attack can have is once I can enforce it, I can use this tunnel as an attacker to disturb the routing, just because, again, I can control the path. I made it much faster, so my packet will be the one that will enforce what the path selection is going to be because of the metric. Okay? It's very difficult to defend against such an attack. The only thing that you can do is just you have to detect that the packet traveled faster, and it's not very easy to do that. Okay? Now, another attack that is also specific to wireless is something that is called flood rushing. If you remember when I was talking about the way the route discovery works, there is a first flood that happens in the network. And if you have, again, an attacker that has the ability to rush these flood packets in the network, maybe using a wormhole, maybe using by refusing to play the protocol, or one thing that you can do also, you can play with the transmission level and the power. And so there are all kinds of things that you can do by refusing to play exactly the way the protocol was specified. Now, if as an attacker, I manage to do this, again, I can control the way path is selected. It's not easy to defend against it. This is actually an attack that is very difficult to defend against. Why? Because the routing design, the design of the routing protocol really required to process only the first flood. If you process more than the one, you have an overhead. So here, there is a trade-off between having a design of the protocol that has a higher overhead or taking the risk of having such an attack. And as we will see soon, this is actually this attack has a very high implication on how much damage an attacker can create in a network. Now, the last thing that I mentioned before, once a node has control over the path, one thing that he can do is just drop packets. And this is, why can the packets be dropped? Well, there can be errors, and that's something that you cannot do anything about it. But a lot of them can be just really deliberately dropping data. And what makes this problem difficult is that in general, in an environment that is distributed, here we have multiple participants, connected in this network. In an environment that is distributed, it is, in particular case, it was proven that it is impossible to figure out if that packet didn't make it because it was dropped or because it was a fault. And there are ways in which you can go around the problem, but at higher cost and by weakening your requirements. Now, this is a summary of the many attacks that can happen and what kind of attackers can we have. But let me tell you a little bit, okay, I also have a list here with related work, but I'm going to focus, I want to tell you more about our protocols. But I'll be very happy to talk with you about, in just one word, there is a lot of work in targeting particular attacks, but there is no protocol that actually tries to cover all of them, particularly the dropping. So detecting that data was dropped usually has a high cost and people avoid to do it. They just say, I'm going to do just authentication and integrity, which is not necessarily bad because those are basic things that you have to have anyway. Now, let me tell you a little bit about this protocol. So what is the goal? The goal is the following. Assuming that I have a source, I have a destination, and I don't make any assumption about how many parts in between them are compromised, but the assumption that I'm making is that there is a correct path between these two guys. If there is no correct or no adversarial free path, there is nothing I can do. But if such a path exists, then my goal is to detect it and to use that to deliver data. That's really the goal of this protocol. And there are several design principles or approaches with respect to designing it. It's still an on-demand protocol. It has a flood request and flood reply, which is the route discovery phase. What is special about it, as I said, we don't make any assumptions about the nodes in between. So the flooding the network on the way there and on the way back, it's really a requirement, because otherwise it may be that you reach only the people that are malicious, and they can drop also the routing discovery packets, and you're never going to establish a path. Okay. The other thing that is different about the approach that we are taking, we are not trying, for example, with respect to wormholes, to prevent their formation. All that we care about in the end is the impact that this can have on the service itself. So if we detect that something bad happens, that's when we are trying to readjust the path and to avoid the links that are problematic. The other thing that we are doing is, because we are not able to pinpoint, I told you about the impossibility of saying why that data didn't make it. We cannot say exactly this particular node is the node that created the problem. Why? Because this guy will say, oh, it's not my fault, it's the fault of this guy, and he will say the other thing, and there is no way you can make a decision. What we are doing, we basically, mark links and not nodes. So with respect to routing, that is fine, because that's all we care about. The other thing that we do, and that's actually the most problematic part, is when the data makes it hop by hop, we have a mechanism in place that prevents any intermediate hop from modifying data that was already put on the packet by previous hops. And that prevents, for example, somebody from making the path looking longer or shorter. And the other thing that the way we achieve or we readjust the path is every link has some metric associated with it. If we discover that on one particular link many packets are dropped, we readjust the weight on that path. And the way we are readjusting the weights on each link, it is done in such a we do this in such a way that we can bound the amount of data that can be dropped in the network. And we bound this logarithmically. Okay. The other thing that I should mention is that once some paths or some links are excluded, they are never out forever. That's where the bounding comes into place. We allow them, if for a certain amount of time they are behaving nicely, we allow them to come back in the network by adjusting again the weight. So this is like an overview of the protocol. We have a route discovery phase that will have as an output a path, and then that's the path that we are going to use to route packets. In case we detect that there's something wrong going on with respect to data forwarding, we had a Byzantine fault detection mechanism that allows us to detect what are the links that are causing problems. And the result of this will be one faulty link or a set of faulty links. And then we have this link weight management mechanism that modifies the weights in a way that it bounds the amount of damage. We get a new list, and then we apply the route discovery. So this is an overview of the protocol. I want to tell you a little bit about fault detection mechanism. So traditionally, one thing first that I forgot to mention is that in the way our path is detected, we know the whole path. So when a source routes to the destination, he knows the whole path. So that allows us, the simple mechanism that, for instance, you can do in this case to see where the data is dropped is to ask for acknowledgement at every hop, like in this picture, which is quite a long, the overhead is quite big because it's linearly with the size of the path. So because we know the path, we can do much better than that. You can actually do an adaptive probing in which you you look at the path like an interval, and you keep breaking it in half to detect where it happens. Now, it's not, or things that you have to take into account is the following. First of all, your adversary can move. So how do you start this? You have to keep in mind that an adversary can move from one point to another. So at the worst case, you keep all the probings going on, because you may have actually more links that are problematic. That's one aspect. The other aspect that I would like to mention is that once you have such a mechanism in place, well, guess what? He can be attacked too. If the attacker detects, he knows that this particular message that goes over the network is a probe, it will treat it differently. He will let the probe go, but he will drop all the data. So because of that, you have to have once we have such a mechanism, we introduce it in the protocol in a way in which we are able to mask that these probes or the acknowledgements, they look like different packets. And there are different ways in which you can do that. And cryptography helps you a lot there. So this is one of the things that I wanted to mention to you. The link management, as I said, basically what we do to give you the details. Basically, what we do, we use a mechanism that is very similar with the way TCP also handles congestion. Every time we detect that there is some loss, we double the link. We double the weight of the link. So this is the multiplicative aspect. Now, if we see that after some time nothing bad happened on that particular link, in order to rehabilitate the link, we decrease it then by 1. So such that over a certain amount of time, our analysis shows exactly how much damage you can bound. How can you bound the amount of damage that an attacker can create? Now, I promise you that I'm going to show you some simulations, and I want to use the time to do it now. So what did we simulate? Well, first of all, so this is not a real implementation. We used the NS2 simulator. We implemented this protocol, and we performed simulations using 15 nodes that were just regular nodes in the network. And then what we played with the number of adversaries that can be introduced in the network, with the types of attacks that they can perform, and where they are positioned. Because it turns out that it's very important where the attackers are positioned and the combination of the attacks that they can create. Basically, we wanted to say, from the adversary point of view, what is the maximum damage where should I be positioned, and what attacks should I do such that I can create the maximum damage? Which means maybe I don't need to compromise too many nodes. Maybe all I need is one node and I will create a lot of damage. So these are details about the way we perform the simulations, but the things that are important are how many nodes are correct, which is 50, and up to 10 can be adversary. So the configurations that we looked at are the following. The most simplest one, so we also want to play with wormholes. So we will also need at some point configurations in which we have 2 nodes. So the configurations that we looked at, one of them is called central wormhole. In other words, in the area in which we are performing the simulations, we put a wormhole that is centrally placed, which means the adversary compromises these 2 nodes, control these 2 nodes, and can perform any type of attack. Then we looked at 2 other more configurations, 2 wormholes placed like that, and the strongest one, which is the last one, you have 5 nodes, and you can have wormholes between each of them, which means that in the last case, what you actually have, and that's so strong, is because you have a network within the network, and the network within the network is controlled by the adversary. And the cross of death name is not my creation. I also thought that was funny, but actually Herb came up with the name. He's good with names. So the first thing that we want you to look at is what is the damage that an attacker can create if he can perform more sophisticated attacks? Is it important or not that an attacker can control more paths or not? The black hole, so in this picture what we did, we took AODV, which is a well-known routing protocol for ad hoc wireless networks. We took our protocol, and then what we did, we played with, for different speeds, what we said, let's look what happens when I take the black hole attack, which means dropping data, and also adding to this the ability that the attacker can perform flood rushing, which means he can control more paths. On the X, we have how many adversaries are in the network. So the ones that are below, you can see how much data actually it's dropped. This is the delivery ratio. So the higher you are, the better, which means that you don't lose a lot of traffic. The lower you are, it's not good. This means that most of all that traffic, how much you dropped is the data, how much the graph goes down, it's the data that you dropped. Not a very good idea, so not a very good thing. So in this case, for example, you can see that if I look at the worst case, which is 10 adversary, I think it's about 50 or 40% of the data makes it. So it's half of it makes it, half of it doesn't make it. But all that is happening here, as I said, is just performing this flood rushing attack. There is no tunneling going on. Now, if I take that wormhole central configuration that I told you about, this is what's going on. Again, in all the graphs, you're going to see AODV and our protocol. Now, for this case, what we did, what happens if you have only a wormhole attack, or if I combine the wormhole with the rushing? Is there any impact or not? Maybe there is no impact. Of course, we look from the perspective of adversary because we want to know how can we defend. So we want to see what's the best. So as it can be seen, look for the last, what's the color? Magenta or lila, or I don't know the color. The last one, you can see that when you start combining, when the attacker starts combining the attacks, he can create a lot of damage. And in this case, there are only two adversaries, only 2 nodes are compromised. So you have a network of 50 nodes in which 2 nodes manage to drop the data delivery to 40%. Let me see okay. The other thing that we wanted to look at is its position, where the attackers are positioned. Is it important or not? From the attacker perspective, if the position is important, he will go for some particular nodes. Otherwise, it's just randomly compromised nodes. So as it turns out, actually, where the position is extremely important, because depending on where the attackers are positioned, they can create much more damage. And also what we try to do, so we look at position. The other thing that we look at, coordination between the attackers. And I think that this is what I had here, yes. So is it important that you have that the attackers coordinate or not? When the nodes are randomly placed, there is no coordination between the attackers. If the attackers can coordinate, actually they can create more damage. And this is what we were showing with looking at the cross of death configuration. It is worth mentioning, I mean, I don't want to say that this protocol is the best in the greatest of the greatest. It's just the first try of looking at, can you do anything about dropping data? So for example, ODSBR doesn't react very well if you have many links, many adversary links in the network. And this is what the complete coverage configuration shows. The more compromised links are in the network, the slower the protocol reacts. Yes, it will find them in the end, but it takes a long time. So it depends on the nature of the application. Maybe the price is not acceptable. So this is what we were trying to show by looking at why we chose this particular configuration. Well, because the transmission range, the way that we chose this configuration such that given the area that we have and the transmission range of each individual node, this network here basically covers all the communication that goes in this area. That's why we call it complete coverage, because basically you cover everything. You missed, I think, that a little bit from the corners of the square, but other than that, the attackers really can overhear all the communication, can reach the point. So this is, again, we are looking at what's random placement with number of adversary versus having the complete coverage. So to give you like a small summary, based on the simulations that we did, there were 2 things that we concluded were very problematic from the point of view of designing the protocol and very, very good for the attacker. And one of them was flood rushing. Actually, in most of the cases, that was the attack that when was introduced in what the attacker could do had a very significant impact on the dropout of the data. Why? Because that allowed the attacker to control many paths. We could perform other attacks and maybe show like how much data goes through that particular node that later on could have been used for traffic analysis. The other thing that we showed in this, which was, as I said, was quite for us was, as I said, from the attacker point of view is good, but from the point of view of people that designed the protocol, for us was a big alarm when we saw that having only 2 colluding adversaries. So as an adversary, you had to compromise 2 nodes. It's true you cared about their position, and just having all those you could reduce AODV delivery ratio to 50%, 51%, which means that half of your data never makes it. And as I said, coming from the distributed system community where the reliability and availability are extremely important, this was something that we weren't very happy with. And in general, most of the attacks we could mitigate, but there are the protocol is not a cheap one. I'm not gonna lie saying that it's very cheap. It has additional overhead. Some of it is just from the fact that you have to process more flood requests in order to avoid the flood rushing attack. That's why ODSBR actually reacted very well to that, and we didn't drop that much traffic. I want to use the last minutes to tell you a little bit. It's still 11:20? Okay, so I'm going to use 10 minutes just to show you how some of these ideas, you can take them and apply them in another environment. And it actually turns out that in the environment that we moved, it was much easier to address some of the problems. So what is this environment? Well, this environment, it's an environment that has a 3G wireless network and also has a multi-hop component. Then now, why do we need the multi-hop component? Well, the promise of the 3G cellular networks were that you could do data, you could do video, you could do images. So you have all these applications that are pretty nice. In such an environment, how does it work? You have a base station, you have a user, there is a direct connection, wireless, of course, between the base station and the user gets authenticated by the base station, that's how the traffic goes through. So it's an environment that is centralized in some sense because of the presence of the base station. Now, the further you go from the base station, the quality of your traffic, the quality of the data and the throughput that you can get is much lower. So one group from UCLA suggested that you can actually go around this problem by having a wireless LAN, a multi-hop network that was playing AO211, which is the wireless, you have the wireless LAN created there, such that when you get too far away from the base station, you can get good traffic, like high bandwidth, just by using the wireless. This can be laptops, for example, and they are using a different type of technology that allows you to get a higher bandwidth. So that was pretty much the idea. And this was proposed, as I said, by a group from UCLA. Now, Bogdan and Yanis came to me and said, look, we think that we can do better than they do. And I said, well, I don't believe, let's see, let's talk. So they showed me they had the protocol that their goal was to get better throughput. And they had a very nice distributed protocol that allowed them, they were building some trees using, they were also using some algorithms that allowed them to have everything very low overhead, decentralized. So everything was nice and I like it, but I asked them, well, you realize that the moment you put the multi-hop component there, your trust model changed. Why? Well, because as long as you had only the relation with the base station, which anyway, if the base station wasn't there, there was no service, it was one type of trust. The moment your data goes through the intermediate hops, from the security point of view, things change. Because you cannot have the same type of trust. So these intermediate hops actually, they're supposed to be users. So these are not dedicated, this is not dedicated infrastructure, at least in the model that was proposed by them. So if they are users, why should you trust them? So that's pretty much how this work started. Then we said, okay, let's look from the security point of view, what happens, what are the implications that we have these relayers here? So how can we look at it from the throughput point of view, because that was the goal of the application. And security is always something that, it's an extra. Whatever service you have there, you'd like to protect that service or that information or that data. So we look at what are the type of attacks that can happen. And besides the ones that we knew about, here in this case, the things that we cared about is how do you decide which is the best rate? Well, it's because nodes usually report. So the way the protocol works, you build a tree, and the tree maintains the residual capacity in the network. That's how you know what is the next best throughput path that you can have there. Well, but how is that built? Nodes are telling how much rate, what is their rate from where they are positioned to the base station, and there are all kinds of implications by the fact that you rely on information that comes from these guys. Well, they can lie about that information. They can lie about their position. So what can we do about it? So these are the bad news. What are the good news? Well, the good news was that the base station was still there. So, and not only that the base station was still there, but the wireless communication, the cellular link between the base station and each user in the network, it's still there, and we could use it as a control channel, kind of. So you use the purpose of the original system without security is that, depending on how far away or close you are to the base station, you are using either the multi-hop or the cellular link. And then when we looked at security, we say, you know what? I like very much the fact that the cellular link is a direct link between the base station and the user. That's a link that can be trusted. So that turned out that it helped tremendously when designing the protocol. So we looked both of how can we prevent people from inflating the rate that they are reporting, and we also look at how can we prevent with respect to data that goes through intermediate hops. The same, one of the things that was in common with the previous protocol, can they drop data? How can we prevent? How can we detect that? There were two things that help us better in this case. Let me go to, so first of all, the overview. So we have a secure routing path maintenance, which basically we maintain this tree. Then we have a secure path reservation because the user requests a particular type of service. This is the amount of data, and this is the commitment that we are making. And the last part that we cared about is how do we do the data forwarding. From the perspective of the previous protocol that I presented, what is interesting, and I would like to spend time on, is the last aspect, secure data forwarding. Not that the others are not important, they're actually quite difficult to achieve, but I want to talk about that just because it is, it shows you how the environment can make a problem easier or more difficult. In this case, it makes it much easier. Why? So how did it work before? Remember, I was doing the search on I have the path, and I was breaking the path, and all the probes were going through the multi-hop, and all the acknowledgement were going through the multi-hop, and all the errors were going through the multi-hop, which means that you have to protect the mechanism itself again. So because the nodes in between could affect or could try to attack this probing mechanism or the error reporting mechanism. In this case, I don't need to deal with that. If I take advantage of this direct communication between the base station and the individual node, I don't need to go through the whole, making the probes look like random data to prevent them from being dropped, making the acknowledgement, because we had all kinds of sophisticated mechanisms to deal with this. So for example, acknowledgement, you don't send only one, you try to, wait for some of them, try to, to put them together or try to piggyback them on data and so on. So in this case, we don't have to deal with that. All that it stays is the same breaking on the path, but the request of who should, that's another thing. How do I ask as a source, when I break the path, I should ask nodes to report. And I said, you report and you report and you report. This packet goes through each hop. So when this happens, you open the door for intermediate nodes to start blacklisting. So you get into all kinds of trouble, and to get around them, as I said, you take advantage of cryptographic mechanisms, but the cost is pretty high. In this case, I don't need to do that. So this is just an example where actually by moving in a different environment, taking the same idea, it turned out that it was much better in terms of the overhead. So this protocol, we didn't implement it yet. We are in the process of implementing it, and we will see how it behaves. There are many things that we still have to deal with, and one of them is verifying that the position reported is correct, or the rate is correct. That we have some solution for it, but it's not 100% correct. It's very difficult to have mechanisms that can tell that this particular position, that a node cannot lie about his position. Okay, that's something that we are looking at. Another problem that is quite big for wireless communication is interference. And when you are selecting what is the best path, most of the metrics today, they don't take into account that you actually can have interference on that channel. And that's very difficult to deal with. So these are the two main things that actually we are looking at. We are also looking at extending this work to other type of hybrid networks. We looked at cellular, but if you really look at the way we operate, the whole network is hybrid. You have a wired backbone, and then you have all kinds of wireless LAN or cellular networks that communicate with this network. And the last thing that we are interested in is mesh networks, which actually changes. So this particular last last application created a revolution starting from the hardware, the way first the hardware is constructed, and the way the very low-level protocols, starting also with the MAC protocol, are designed. So this is something that we would like to, again, to look in this environment on how do you do routing and maybe more sophisticated applications, starting with the strongest attack model. Because once you have some ability of dealing with that, it's always much easier to relax than to make your, start with a weaker model and make it much stronger. So this is if you want more information, we have a webpage. This is the webpage where you can find more papers, the papers that I cited here, and other work in the wireless that we are doing here and at Purdue, with also collaborating with people from EC. So this is what I want to tell you. If you have any questions, thank you very much.